how quickly they forget. What does a sprinter use for its primary source of energy? Glucose or fatty acids?
Glucose.
What does Dr. Stickney, when she ran the Boston Marathon on Monday, what did she use as her primary source of energy?
Fatty acids.
Fatty acids. Why?
Slower.
What?
Slower.
What's slower?
When they kick in.
What's
Like when
The breakdown takes longer.
kicks in.
of what?
Okay.
Fatty acids, right? So extracting energy from fatty acids, going through the citric acid cycle is slower. So this lets the liver deliver energy to peripheral tissues, right, in an easily metabolizable way, but it's still a way that has to go through the citric acid cycle. And so it still suffers from that kinetic problem that fatty acids suffer from. You can get lots of energy, but getting it is slower than it is if you just break down glycogen and use glucose. Okay? Any questions about that?
When we so when we started it, we started with the 2 acetyl-CoAs, and then this was from the acetoacetate. So like one of the acetyl-CoAs stayed in the liver,
Right.
and the other one was transported out.
Well, the
Acetoacetate was.
the beta hydroxybutyrate was transferred out.
Is there a reason, like, are we not able to just deliver acetyl-CoA to the tissues?
No, there's not a mechanism for this is the mechanism to deliver acetyl-CoA equivalents
Okay.
around. Okay? So, now let's talk about fatty acid biosynthesis. And so this slide, I like this slide because it contrasts beta oxidation of fatty acid with biosynthesis of fatty acids. Okay? So, if we're oxidizing fatty acids, first that oxidation occurs in the mitochondria. Right? So oxidation occurs in the mitochondria in cycles. The biosynthesis of fatty acids occurs in the cytoplasm. Okay? The acyl group carrier in oxidation is coenzyme A, with carnitine helping us get it into the mitochondria. In biosynthesis, there's something called the acyl carrier protein. ACP is the acyl carrier protein. Okay? In beta oxidation, we use FAD and NAD as the electron acceptors. In biosynthesis, we use NADPH. Okay? The product here is acetyl-CoA. Here, our 2-carbon donor is malonyl-CoA. And so we'll talk about how we make that. We use a 3-carbon molecule as our 2-carbon donor to start fatty acid biosynthesis. So we'll talk about those differences. Okay? Are we good with that? All right, so first we have a problem. Houston, we have a problem. That is, acetyl-CoA, even if we're getting it from carbohydrate, right? So remember, fatty acid breakdown is inhibited when we're doing fatty acid synthesis, right? That wouldn't make much sense. So when we're making fatty acids, most of the time we're making them from non-fatty acid starting materials, right? If you've got extra fatty acids, your body just stores them most of the time, right? So what are the primary non-fatty acid starting materials that we can use to make fatty acids?
Amino acids. acids?
Amino acids would be a big one, right? What else? Oh, come on. What are you not supposed to eat a lot of or you're going to get fat? What?
A lot of things.
A lot of things, but what's the big thing?
Carbs.
Dr. Cutler is our prime offender.
Candy.
Candy, sugar, right? Right? So, in the liver, if you have excess glucose, when the liver does either the pentose phosphate pathway into glycolysis or glycolysis itself, it's often to send that into the mitochondria to make acetyl-CoA. That acetyl-CoA is going to be used for fatty acid synthesis, not the liver's own needs. Right? So this is where they, what do I have? The Welch's fruit chews that I have sitting by my chair at home, right? When I'm sitting there doing nothing except grading papers and eating little fruit gummy things, right? This is where most of that is going. Going into my liver. I'm not using a ton of energy. I just ate a big supper, so I've got plenty of other fatty acids around to run my resting oxidative metabolism. So once my liver decides it's full of glycogen, it signals we've got enough glycogen, do something else with it. It's metabolized through glycolysis, made into acetyl-CoA, and used to make fatty acids. Right? Okay, so how do we get the acetyl-CoA that is in the mitochondrion, how do we get those equivalents out of the mitochondrion so that we can do fatty acid synthesis in the cytoplasm? Okay, that's what this is about. So we use the citric acid cycle enzyme, citrate synthase. You take oxaloacetate and the acetyl-CoA, you make citrate. There is a citrate transporter in the mitochondrial inner membrane. Okay? There is a citrate transporter. So citrate can get out. Now, what have we talked about citrate in the cytoplasm before? What have we talked about citrate in the cytoplasm before? We have. Trust me, we have. Citrate was an effector of something. Oh, yeah. Nope. Good guess. Not that one. No.
That complex?
Yes. Citrate was one of the effectors of PFK. Right? Phosphofructokinase. So, citrate would inhibit phosphofructokinase. Okay? So now we have to think about that. Where did we say we were getting this acetyl-CoA?
Sugars and amino acids.
Yeah, sugars and amino acids. Let's focus on the sugars thing. But this citrate coming out is also going to inhibit PFK. What's that going to do to glycolysis?
Stop it.
Yeah, it's going to slow down glycolysis. So what must be happening then to make the acetyl-CoA? How must it be getting through the process?
DPP.
Got to go through the pentose phosphate pathway. Why would the liver want to shuttle it through the pentose phosphate pathway?
To generate NADPH.
To generate NADPH that eventually we're going to need to use to synthesize the fatty acids. That's pretty slick, right? So this citrate coming out as part of fatty acid synthesis is also the signal that is really telling the liver, don't send it this way, send it around the long way because we need the product NADPH. Right? So, citrate gets out. Now we end up with an enzyme, ATP-dependent citrate lyase. Now, I don't know the mechanism of this one, but let's see. If it's a lyase, what do we know? We just talked about lyases. What do lyases do? What did it just do? I just said it like moments ago.
You create a carbanion.
Okay, so this is going to leave us a carbanion, and the catalyze, if we start with an alcohol here, and we end up with a carbonyl, what kind of reaction was that? Start out with single bonds and you end up with a double bond. What is it? An elimination, right? So it catalyzes an elimination, right? In this case, it's ATP dependent. So we end up with, the ATP dependence is probably to put the coenzyme A on the acetyl-CoA. Right? I'd have to look at the mechanism. So now we end up with oxaloacetate. This acetyl-CoA is now in the cytoplasm. It can be used for fatty acid synthesis. The oxaloacetate is reduced in the cytoplasm to malate. The malate is oxidized, and the resulting oxaloacetate decarboxylates as part of the malic enzyme. You get pyruvate. Pyruvate can be transported back in. We get pyruvate carboxylase to recreate our oxaloacetate. There is our shuttle cycle to bring acetyl-CoA into the cytoplasm. Okay? We're good with that? Reed looks concerned.
So we're just doing this cycle to move acetyl-CoA into the cytoplasm?
That's the whole point.
Okay.
Yep. And to move an acetyl-CoA into the cytoplasm essentially takes 2 ATPs worth of energy, one in the mitochondrion, one in the cytoplasm. But remember, we're doing this when we're in a well-fed state, so there's plenty of ATP around, right?
Why would you move it out back to the mitochondria?
Why would
Why would
you
you move back out?
move what back out?
Like, why would we transfer it to pyruvate and then ship it back out?
No, this is out here. We just have to get as many of the carbons back into the cycle as we can. So this is recycling 3 of the carbons that we started with. Okay? Another thing this cycle does is convert, right, under these conditions, the combination of these 2 enzymes converts NADH in the cytoplasm to NADPH in the cytoplasm. So part of the shuttle also creates more NADPH that we're going to need for fatty acid synthesis.
What's the enzyme that takes the NAD to NADP?
This one? What?
NAD to NADP? When does it get phosphorylated?
It doesn't. I mean, it does elsewhere in the synthesis. NADH, right? Electrons are taken away from NADH when malate is reduced. Those electrons are given to NADP when it's oxidized. Right? So it's a transfer of electron equivalents. Okay? We good with that? All right. So there's our transport out. Now,
This kind of might be a dumb question. So is the only difference between